liquid state. In general, liquids can be obtained from gases by cooling the latter below their respective critical temperatures, followed by the treatments of high pressure. The effect of cooling is to decrease the thermal energies of molecules, and the effect of high pressure is to decrease the volume of the system so as to allow the molecules to come closer, thereby increasing the binding energies amongst them. Alternatively, liquids can be obtained by heating solids up to or beyond their melting points. In solids, molecules do not possess any translational energy but possess only vibrational energy. The binding forces amongst them are very strong. The effect of heating solids is to impart sufficient energy to molecules so that they can overcome these strong binding forces. Thus, we see that the properties of liquids lie in between those of solids and gases. For example, liquids are less compressible than gases, but a little more compressible than solids. They are less dense than solids, but more dense than gases. The two important properties of liquids, namely fixed volume but no fixed shape, arise mainly because of the following two facts. 1. The energies binding the molecules are large than their average thermal energy. 2. These binding energies are not strong to stop the motion of the molecules altogether, as in the case in solids, with the result that molecules can move from one place to another but cannot escape from the liquid unless they are present at the surface. In this section, we will discuss only three properties of liquids, namely 1. Vapor pressure, 2. Viscosity, and 3. Surface tension. The origin of these properties in liquids is basically due to the existence of strong intermolecular attractions. Suppose a beaker containing a liquid is placed in an evacuated vessel. See figure. Let the latter be connected to a manometer so that any pressure that is developed in the free space can be measured. After some time, it is found that the manometer records a constant pressure. This pressure is known as the vapor pressure of the liquid. Before making an attempt to understand how the vapor pressure arises, we will have to consider the following two facts. 1. The molecules of a liquid, like those of gases, have different kinetic energies. The distribution of speeds amongst molecules follows Maxwell-Boltzmann distribution. Figure shows such a distribution at two different temperatures. The most important point to be noted in these distribution curves is that the fraction of molecules having higher speeds increases with the increase in temperature. 2. If we consider a molecule in the bulk of a liquid, it will be surrounded by other molecules in a symmetrical manner. Thus, the forces of attraction on this molecule by the molecules present on one side are completely balanced by the molecules present on the opposite side. Hence, the net force of attraction experienced by this molecule will, of the whole, be zero. It will move as if there existed no forces of attraction on it. However, the situation is altogether different at the surface of the liquid. Figure. there are a large number of molecules towards the liquid side of a molecule than towards the open space above it, with the result that this molecule experiences a net force of attraction in the downward direction. Effect of temperature on vapor pressure. On raising the temperature, more and more molecules of a liquid will have energies equal to or greater than the critical energy, which is just sufficient to overcome the forces of attraction between the molecules. As a result, a large number of molecules can leave the surface of the liquid, which will consequently have higher vapor pressure. Thus, the vapor pressure of a liquid increases with increase in temperature. The variation of vapor pressure of liquids with temperature is of the type shown in figure, with the highest and lowest limits corresponding to critical point and triple point respectively. Surface tension. Origin and definition of surface tension. It was seen during the study of vapor pressure that the molecules at the surface of a liquid experience a net inward pull because of the larger number of molecules towards the liquid side than towards the vapor side. There is a tendency on the part of surface molecules to go in the bulk of the liquid. The surface of the liquid is therefore in some sort of tension, and it tends to contract to the smallest possible area in order to have the minimum number of molecules at the surface. It is for this reason that the surface of a liquid is spherically curved, since the surface area is minimum for a given volume in the case of a sphere. If the area of the surface is to be extended, then one has to bring more molecules from the bulk of a liquid to its surface. This will require expenditure of some energy because work has to be done in bringing molecules from the bulk against the inward attractive forces. The amount of work done in increasing the area by unity is known as the surface energy. The larger the forces of attraction amongst the molecules of a liquid, the larger will be the net inward pull. Thus, the amount of work done also increases. Thus, the surface energy can be used to define these net inwards pull. It is customary to define these inward pull in terms of the surface tension. The latter is defined as the force acting along the surface of liquid at right angles to any line of unit length. Unit of surface tension. The unit of surface tension is that of force per unit length. In SI units, it is expressed as Newton per meter. Effect of temperature on surface tension. Since the forces of attraction between the molecules of liquid decrease with an increase in the temperature, it follows, therefore, that the surface tension will decrease when the temperature is increased. Origin of viscosity and its definition. It is a common experience of daily life that different liquids flow at different speeds. For example, water flows with greater speed than glycerol. Obviously, some sort of internal friction is operating which checks the flow of liquids and which varies from liquid to liquid. This internal friction in the case of liquids is primarily due to forces of attraction between the molecules. If we have a laminar flow of liquid in a tube, then the velocity of the layer just in touch with the side of the tube is zero, and it increases as we proceed towards the center of the tube. Thus, there exists what is known as the velocity gradient between different layers of the liquid. Due to greater intermolecular attractions amongst molecules of a liquid, the molecules moving in any one layer will tend to impede the movement of the molecules in the adjacent, faster-moving layer. As a result, the velocity of molecules in the faster layer decreases. The internal friction that resists the flow of a liquid can be measured in terms of the tangential force that is needed to keep the speeds of different layers constant. This force F depends upon the following factors. 1. It is directly proportional to A, the area of contact of two adjacent layers. The larger the area of contact between the two layers, the large will be the effect of intermolecular attractions. Hence, the decrease in speeds will be more. Consequently, a large force is required to maintain constant speeds. 2. It is directly proportional to dx, the velocity difference between two adjacent layers. The larger the velocity difference, the larger will be the force required to maintain the difference a constant.